Addiction is frequently described as a chemical imbalance. Look at the inner architecture of this 3D model as the outer cortex strips away. We are looking at the brain's physical anatomy. Traditional two-dimensional fMRI slices capture flat cross-sections of neural activity. These slices cannot map the depth and volume of the damage, requiring us to evaluate the brain in 3 dimensions to see the full scale of the changes. Deep inside this volumetric space lies the specific neural network governing this behavior, the mesolimbic system. This 3D spatial wireframe isolates the 3 interconnected pillars of that system. We have the ventral tegmental area, or VTA, projecting up to the nucleus accumbens, which then connects outward to the prefrontal cortex. Recovery requires a literal physical reconstruction of synaptic density and receptor availability, unfolding over a strict biological timeline. Treating behavioral addiction requires understanding the biological speed limits of this 3-dimensional rebuild. To track this repair process, we map the brain's chemical topography in 3-dimensional space. Volumetric state mapping visualizes the transition from a chemically depleted state back to baseline equilibrium. This recovery operates on asynchronous temporal gradients, with different regions repairing at different speeds. Basal dopamine volume, the fluid neurotransmitter, normalizes rapidly once substance use stops. However, the physical reconstruction of the dopamine receptors required to process that fluid is delayed. These side-by-side area charts plot both variables. The left chart shows a steep recovery curve for basal dopamine volume. The right chart shows a heavily delayed recovery curve for D2 receptor binding potential. The physical receptors represent the actual bottleneck preventing clinical recovery. Evaluating a patient's recovery by checking baseline dopamine production ignores the mechanical reality. The fluid is present, but the brain lacks the physical hardware required to process it. On day 1 of abstinence, the perspective zooms deep into the VTA-NAAC pathway. This spatial view shows the VTA-NAAC synapse. Chronic substance exposure has caused a downregulation of D2 receptors within the striatum. The blue and purple on this volumetric heat map indicate low binding potential, driven by a sparse receptor population. This creates a biological paradox. Basal dopamine is present in the synaptic cleft, but the hardware to receive the signal is missing. Without enough D2 receptors to catch the dopamine molecules, signal transduction is blocked. The brain's reward center is effectively silenced. This lack of physical hardware correlates with the clinical presentation of acute anhedonia. The patient experiences numbness because the biological mechanism for processing reward is offline. Overcoming this phase requires the slow synthesis of new proteins to physically build new receptors. Early relapse risk is driven by this physical inability of the striatum to process reward signals. Advancing the clinical timeline, we reach a recovery window between weeks 4 and 12. This diagram plots the VTA-NAC synapse across a 12-week timeline. Watch the receptor icons populate within the nucleus accumbens. As D2 receptor density increases, the local heat map shifts from cold to warm colors, indicating higher receptor availability. Executing this synaptic remodeling requires significant cellular energy. This energetic output has a spatial limitation. It solves the immediate, localized chemical deficit within the striatum. While the striatum repairs, higher-order brain regions continue to show structural deficits. The acute chemical deficit resolves by month 3, but the patient remains vulnerable. The top-down behavioral regulation systems are still structurally disconnected from the reward center. Broadening our spatial focus, this microscopic view travels from the deep brain toward the dense cortical layers of the prefrontal cortex. The prefrontal cortex relies on glutamatergic projections to act as the brain's brakes, providing executive control over the mesolimbic pathway. During the first 3 months of abstinence, these connections are structurally weak. This 3D structural view tracks the pathways connecting the PFC down to the striatum, moving past month 6. Notice how the vector lines representing glutamatergic projections visibly thicken and increase in density as they reach downward. This delayed secondary rewiring phase is driven by neurogenesis and synaptic pruning, reinforcing the physical pathways used to suppress cravings. The increased density of these glutamatergic pathways correlates with the return of executive control and resistance to cue reactivity. This glutamatergic recovery requires over a year to complete, a much longer timeline than the dopaminergic repair cycle. Behavioral regulation depends on this asynchronous secondary rewiring. Recovery is biologically bound to a timeline of months and not just days. We can now view the integrated 3D volumetric model of the combined mesolimbic and cortical systems at month 14. These split-screen models provide a direct spatial and chemical comparison. On the left is the day 1 depleted state, with sparse D2 receptors and thin PFC pathways. On the right, the month 14 state shows dense cortical pathways, multiplied receptors, and warm volumetric heat maps. The PFC, VTA, and NACC have now established a stabilized synchronous firing capacity. This result is the product of asynchronous timelines. Dopaminergic receptors fixed the acute deficit early, while glutamatergic pathways secured long-term behavioral stability later. This 3D framework translates abstract behavioral milestones into quantified structural data. Clinical timelines are bound by the physical speed limit of protein synthesis and synaptic growth. Aligning clinical expectations with this underlying biological reality transforms the entire process of recovery into a measurable physical reconstruction project.